Good afternoon, everybody. So my name's Mike Weiner. I'm part of the CAT team. We developed this presentation in memory OLTP and Columnstore customer deployments with two gentlemen, Jack Freeman, who's here from Getty Images, and Ayad Shamot, who's from Care Group. There's a little star by Ayad. He definitely helped us develop the presentation. Unfortunately, he had a family emergency and is not able to join us today. So I'll be talking through his scenario a little bit on their deployment. So just before kind of quickly getting to the agenda, I wanted to give you guys an idea of my team and what we do. So who is SQL CAT? SQL CAT stands for the Customer Advisory Team. And my team, based actually all over the world, but with a number of resources in Redmond, is part of our Microsoft's Cloud and Enterprise Engineering team. So the SQL Server team is part of that team. For SQL CAT specifically, we're focused on working with customers in the technology scope that is SQL Server. So from the Microsoft SQL Server perspective, that's SQL Server on-premise. That's SQL Server in VMs in our Azure cloud. That's Azure SQL DB, which is our PaaS offering in Azure. And the newly announced SQL DW offering as well in Azure. And for our team, a lot of our focus in working with customers is on technology adoption programs and private preview programs. So SQL Server 2016, Azure SQL DB v12, and some of the newer features and components that are coming out in the SQL space from Microsoft. Having said that, if we backtrack a little bit, and a lot of this session is we worked with customers very early on, including Getty and Care Group, who were early adopters of SQL Server 2014. And so we have a lot of learnings and feedback to give you from there. So again, just a little bit more on our team. We have three primary goals and objectives. The first is working with customers, customers that are testing out new features, testing out new functionality, and pushing some of the limits of our products. We want to make them successful. And in doing those, in working with those customers, we get to learn a lot about how the product is used in the real world as well. We try and take those lessons learned and that information back to the product group to improve the product as a whole, and we try to deliver that as well to you as the community through either conferences such as this or through our blog site as well. We have a number of white papers and blogs that we produce as well. A few of them, actually, I point to at the end of this session. So I will do a quick teaser that if anybody is interested, in particular in working on some of these new technologies, SQL Server 2016, Azure SQL DB v12, and some of the new functionality there, we're definitely very interested in talking to you and always looking for new early adopters to work with. And the way that we work with customers is we will typically do architectural reviews, design reviews. We have a lab in Redmond where we can do scale and perf testing. And from the CAT perspective, customer advisory team perspective, we're free resources. We don't charge for anything. So the agenda, couple quick questions for everybody. Who has attended one of the in-memory OLTP sessions? In-memory OLTP overview? Okay, that's a good majority. What about the Columnstore sessions? Okay. So we'll go through a few of the intro slides pretty quickly. Who has worked or deployed in production with in-memory OLTP in SQL Server 2014? Okay. 1, 2.
2.
What about the Columnstore? 2012? 2014? Okay. Great. So I'm just going to do a quick overview. It's a few slides. Just probably touch on a few quick points. I think as you guys have been to the sessions, these slides will look probably pretty similar to what you've seen. Then we'll talk about real-world customer experiences. So I will present the care group scenario. Jack will present Getty scenario as well. Very open to questions as well. If we have to defer some things till later, more than happy to sit around and talk afterwards as well. And then we've worked with a number of customers, so I have some further lessons learned on kind of broader deployments or other things to consider in working with both of these technologies. Okay, so if I ask, everybody's seen this slide then, I guess? So for the in-memory OLTP architectural pillars, just quickly want to go over the main constructs of that. Again, this is main memory optimized. So if you think about the objects that you create in an in-memory OLTP environment, the first one would be a memory optimized table. And again, it's at a table scope, not a database scope or anything like that. So I could create a memory optimized table. Again, we don't have any pages similar to the traditional relational database or disk-based tables that we'll call it. We just have direct row pointers in memory and do some row versioning to help out with the concurrency control and be able to scale in that sense. Indexes exist only in memory, so there's no rights to the transaction log for index updates. They do not exist on any files on disk. No buffer pool, no write-ahead logging. It's a stream-based storage mechanism because we do maintain full durability if you want it for memory-optimized tables. We actually support two constructs, that schema and data, which is fully durable, or schema only, in which we'll only recover your schema if there's a server failure or an instance failure. So by creating memory-optimized tables, I get a lot of these non-blocking execution constructs, multi-version optimistic concurrency, lock-free, latch-free data structures for this. The second construct is natively compiled store procedures. Again, that's aggressive compilation of T-SQL, dramatically reducing the instruction set, and it's at compilation time instead of runtime. So we can get tremendous efficiencies there and ultimately low latency in reducing that code execution. And then a big value prop that we consider is the fact that it's built in. So you get HA, you want to integrate it into always-on availability groups, fail over cluster instances, you can do that. Same manageability through Management Studio, same T-SQL syntax, etc. For in-memory column store, again, typically data stored as rows, very ideal for efficient operations of a small set of rows. For Columnstore and the Columnstore in SQL Server 2014, just if anybody did have experience or had seen stuff in 2012, the Columnstore in SQL Server 2014 clustered Columnstore index, now updatable. So that's what we'll be talking about here. Again, the data is now stored as columns instead of rows. So this is much better and allows for a lot of efficiencies, in particular for data warehouse type workloads and queries. We have the column store, and we talk about the column store under the in-memory name brand or moniker. Although it does actually exist on disk, we have records for the column store components on disk. And so one of the big things you get with in ordering data is improved compression. So you can get a significant amount of compression on disk for your objects. And you'll see that as we go through some of the customer examples. Quick question. Yes.
The OLTP memory or OLTP,
yeah.
How about you write to the disk? Would that be a slower process? You have to move that ahead. You have to wait for the I/O. Right?
Yeah. So the question is on in-memory OLTP, is disk still a potential concern? Yes. So I have a slide a little bit later on that actually shows the primary components that you want to think about. But if you are doing schema and data, absolutely I/O to the log is still a big consideration there. So again, we get improved compression. Typically, when we're ordering in a column format, particular columns will have a lot of redundant data, so we can get some significant compression gains there. As well, When we're fetching, we're no longer pulling up pages. We can, if you select on particular columns, we can just pull those columns into memory. We have some improved performance, again, in having more data that can fit into memory, and we have certain operations that are basically optimized to take advantage of memory. In particular, batch mode operations instead of row mode operations, where we can pull sets of data in batch mode into memory instead of single rows at a particular time. And again, this is just a benchmark that we did with the TPCH workload on data warehouse workloads. So care group. So we'll give a little bit of background. We'll talk about the scenario in terms of how they've deployed SQL Server 2014, and then we'll talk about some of the lessons that we learned through that deployment. That's kind of the model that we'll go with. So a little bit of background on Care Group. This is one of the top 5 largest healthcare systems in the United States. It's comprised of 4 Boston-based academic medical centers and community hospitals. Has about 16,000 employees, about $2 billion annual revenue. They estimate around 150 mission-critical Tier 1 apps that they're managing and working with. They overall store about 2+ million patient medical records. And they're very proud, and as they well should be, that they were ranked #1 technology innovator in the US by Information Week in 2012. Very early adopters and on the cusp of technology. So let's talk a little bit about their system background. They had a security system that they have where they're collecting all the security event logs from their Active Directory domain controllers. The goal is to report any anomalies or suspicious behavior on their network. The details of this particular application, basically any event that's occurring in the domain controller needs to be logged, collected, and then ultimately surfaced for reporting. Ideally, they want much more real-time reporting on this type of scenario. Their overall process, and we'll have a slide on this next, a visual graphical slide. They are ingesting large amounts of data. They need to parse, cleanse it. They ultimately were aggregating it for reporting purposes so that users could query it, actually mostly through reporting services type reports. The system handles around 5 million messages a day. The database size was about 110 gig on disk, of which 90 gig is in one particular table. So their goal, the system initially was on SQL Server 2008. The goal in adopting SQL Server 2014 was really to achieve closer to real-time information and reporting. So the bottlenecks in the system, the first one was basically data loading and ingestion took too long for them. In some particular high workload instances, they had an application that would basically push this data into SQL Server database. That application would just grow and grow in terms of memory as it was holding on to transactions because they couldn't ingest the data quick enough. Latching and contention, in particular, as they were parsing, cleansing, and summarizing data. Again, a heavy kind of write workload, update workload with a read workload on top of that was causing problems in terms of the time that they would take to execute that. And then their goal was to have any improvements to the end user query response time. So this is the system event log flow. Again, Active Directory, domain controllers. And from there, they had a client application that was basically sending info into a database. So they had 2 particular tables here, system event and system event detail. System event detail being about the 90 gig size table. Queries were taking somewhere between 60 and 90 seconds to do their larger aggregating reported queries. Again, about 10,000 inserts per minute through the system, kind of on a steady state. There's the 200 million rows, 90 gig size, and the system event detail. So again, this was 2008 R2, about 110 gig on disk. So upgrade to SQL Server 2014. In doing that, they moved the system event table specifically to a memory optimized table. They moved the system event detail table into a clustered column store index table. So same database, two different tables, one memory optimized, one clustered column store index. The 90 gig size on the system event detail table was reduced to 60 gig. And so for their overall environment on their database, they actually reduced down to 80 gig on disk. Query time went from 60 to 90 seconds on average to about 10 to 20. So let's jump down a little bit more into their in-memory OLTP implementation. Clustered column store index, actually should mention, again, they implemented the updatable clustered column store index. They did daily partitioning, and I think they're averaging keeping about 3 months of data in the system event detail table. So they utilize partition switching to swap in and out that data. Again, keeping about a 3-month window. For memory optimized tables, they did not move the entire database, obviously, into in-memory OLTP. They actually just chose that one table where they had a lot of the contention points and moved that into the memory optimized table, just that event system table. The size in memory is about 20 gig. The durability that they chose is schema and data. They did want it for recoverability. We talked about the different table options for memory optimized tables. And for indexing, they used 2 indexes. So they had a hash index on an identity column on their primary key. And again, because they were basically pulling that data from the memory optimized table into the column store index via insert select, they had a non-clustered index on a date time column. They did not go to natively compiled store procedures, in particular because the types of queries or the types of calls that they were doing were from a memory optimized table to a disk-based table, and natively compiled store procedures can only be executed on a memory optimized table. In terms of development, there were no application code changes that they had to do in implementing this. Their deployment took under a minute in terms of application downtime. That was basically to create the memory optimized table, load that table, and of course create the clustered column store index. And ultimately, they had an aggregation step that was just before summarizing that data, and they were able to completely eliminate that. So let's talk a little bit more about some of the gains that they got. For data ingestion, the data was no longer delayed into the database. They're now able to handle all the high spikes that they do in their workload. They definitely feel like they have a buffer, and they're very confident they can actually handle much more workload if they need to. In terms of their parsing, cleansing, and aggregation of batch processing, they got no more. They had no more contention in terms of their job execution, and they were able to basically reduce. So they used to have to run each job on an hourly basis. They were able to reduce that to every 5 minutes. And they were ultimately able to remove the entire aggregation component because column store index was able to basically get them that data much quicker without having to do any type of pre-aggregation. For query performance, they got between 4 and 6x gains, again, going down from the upper echelon, 60, 90 seconds down to 10 to 20 seconds. And their data size on disk was reduced, primarily or wholly because of the clustered column store index. So let's talk a little bit about the lessons learned. And this one, we're going to talk a little bit about primarily the lessons learned with in-memory OLTP. And then Jeff will talk a lot about the lessons learned for kind of column store implementation. So the first consideration as they were going through their process and their testing and their deployment was it's really critical to identify the objects and data which can benefit from in-memory OLTP. So Care Group utilized the tool set that we include with SQL Server 2014. We typically call this AMR, or as Analyze, Migrate, and Reporting tool set. That can help you analyze where the points in your current application and workload may benefit from in-memory OLTP, both for memory optimized tables and natively compiled store procedures. A limitation of memory optimized tables is that they only support a row size of 8060 in SQL Server 2014. We also don't have any support for lob data types in SQL Server 2014. Care Group did have this in their environment. They were very interested in going to memory optimized tables, again, to get all the benefits there. And so they recognized that they really actually had created columns that they didn't really need of padded length. So they reduced that to Barcon 4000, got that in row to take advantage of the memory optimized tables. It's very important to pick the right indexes based on your production workload. Hash indexes and querying hash indexes can perform very different than typical B-tree indexes. Again, also with our range indexes, our non-clustered indexes for memory optimized tables, they aren't doubly linked lists anymore, so there are some considerations around that. So kind of understanding the differences between those, they reviewed some DMVs that they had to basically understand their workload a lot better and pick the correct indexes for their particular workload. When they were initially doing testing, it didn't work out so well. And then by changing the indexing scheme to match what they really needed, they were able to get much better performance. So sizing memory and storage is somewhat different than disk-based tables. Within memory OLTP, we have the concept of a dedicated resource pool for the memory optimized objects. So the recommendation is to use that. And what you really need to do a little bit differently is take into consideration a few more things. So you need to think about basically the size of the internal memory structures, in particular if you're doing hash buckets, right? We take up space in memory when you create those hash buckets. When you delete a particular row, that row still needs to be garbage collected. In particular as well, if you're querying that row version, we'll keep that in memory. So it's not automatically just garbage collected from memory. So some of the considerations about your workload, you just need to think about that differently. And then ultimately on disk, our allocations are different, right? We're no longer allocating based on pages. We have this streaming I/O and these data and delta files for memory optimized tables. And the recommendation there is to basically allocate about 3 to 4x what you see in memory on disk for the size if you have schema and data tables. And then recovery performance is dependent on disk and file layout. This depends really on the sequential I/O of your disk device, and there's an article that is pointed to here that talks about some of the considerations there. So with that, I'll turn it over to Jack to talk about Getty's implementation. Oh, okay, I forgot. I actually asked people to do this. So I wanted to quickly talk. Care Group and Getty are both testing SQL Server 2016 as part of our technology adoption program. So I just wanted to give a quick feedback on what they're seeing. Again, some of these results, in particular performance, things may change. So Care Group is testing a different application with Columnstore. This is primarily an application around patient health. They're looking solely at the Columnstore index and the enhancements around that. They migrated a number of tables. This is kind of a batch-based system where they are doing a lot of queries on source tables to enter it into a big destination table. They added Columnstore indexes to 3 of those source tables. They did 2 clustered Columnstore indexes. Third, in SQL 2016, the non-clustered Columnstore index is also updatable. So they added non-clustered Columnstore index to one particular table as well. And so far, they're getting about 2x gains in their data movement from source to destination by using the Columnstore index there. The other feature they're going to look at in 2016 is row-level security.
Hi, I'm Jack Freeman. I'm the Senior Manager of the Enterprise Data Warehouse for GettyImages.com. Getty Images is the world's leader in visual communication. What I mean by that is that we have networks of photographers and companies that we work with. We ingest their assets. We have over 170 million digital assets. These are in stock photography, editorial images, videos, music, audio, and more. Our best-in-class photographers and imagery help customers produce inspiring work, which appears in basically in just about anything you would look up on the internet these days, print, any type of news sources, ad campaigns, you name it, we pretty much are there. We also have a lot of advanced search and image recognition technology, which makes it very easy for people, for our customers, to discover the images that they're looking for that they need to incorporate into their projects. My focus, being the Senior Manager of the Enterprise Data Warehouse, is all on data warehousing. So even though our company ingests petabytes of images and video, the data warehouse has nothing really to do with that end of it. Our focus is solely more on things that you would see in any business, such as order information, product information, CRM information, phone information, whatever system that exists within the company, we basically pull the data into the data warehouse. So the data warehouse itself consolidates data from lots of heterogeneous sources, and we pretty much don't say no to any type of source. So we ingest SQL Server data, Oracle, MySQL, NoSQL. We'll read JSON, XML. We integrate with REST APIs, SOAP APIs. If there's something out there that's data, someone wants a report on it usually, in which case we need to ingest it in the data warehouse and integrate it with our consolidated data warehouse. The Enterprise Data Warehouse is integrated with over 54 systems and databases of Getty Images. And users access the data in the data warehouse generally by going through Microsoft reporting services for canned reports. They may use Excel tabular models or our legacy multidimensional OLAP cubes. We also have SharePoint integration, so we have some Office 365 pages with web parts that are really pulling from Excel spreadsheets that are being fed by tabular models for dashboard reporting. We send reports out in the form of emails to customers, internal customers, I should say. So those could be HTML emails, so they just see the email and they take their action off of it, or it might be attachments. And then other applications are fed by the Enterprise Data Warehouse. So we may load data off to somewhere which then gets ingested into another system, such as that may need information that would be otherwise very difficult to get. For instance, if you have like some data points about customers and a system needs it, but the data exists in 8 different databases in 2 different data centers, then the Enterprise Data Warehouse often will be a place to turn to get that data in the place it's needed. The Enterprise Data Warehouse at a very, very, very high level consists of a single primary Enterprise Data Warehouse server. It's 32 cores, 384 gigabytes of RAM. It is on EMC Extreme IO, which is a flash on SSD solution. And the server is, I believe, no more than 2 years old at this point. This is the primary server where data goes into. This is where all the ETL and the heavy lifting goes. So SQL Server agent jobs orchestrate running SSIS packages that load the data in the data warehouse. All of our reporting layers, though, do not hit that server. We have a second server that's in an entirely different data center. It's one's in the West Coast, one's on the East Coast. So the data is synced to that secondary data warehouse through always-on availability groups using asynchronous replication. We don't use synchronous replication. It'd be a very bad idea with that many miles between us, because that would actually have an impact on our ETL. We use it for 2 purposes. One, for DR. So if our main site, our main database server goes down, we can fail over to our secondary and continue working and delivering our services to our internal customers. We use it for, you could argue, high availability for maintenance purposes. If we need to do maintenance on a server, then we'll take one server out and we'll put all the workload on a single server while we do maintenance on the second server, then swap them. Bring that second one up, switch all the workload over to it, do our maintenance on the primary. All of our analysis services cubes, all of our analysis services models, or tabular models, our reporting services reports, as well as some other legacy reporting systems, all read from the readable secondary. Okay? That allows, a while back we had all of our workload on a single server, and we found we were using all 32 cores and we're running at 95% CPU utilization. We were running out of memory. Once we split the workload across 2 servers, we now had 64 cores to do that workload under, and we found that our servers are now in a more healthy state. The enterprise data warehouse has grown considerably over the last few years. About 3 years ago, we completely rebuilt it from the ground up, completely changed the architecture. We used to have development, test, stage, production support. We're building another environment. We were using something like 25 terabytes of disk for the data warehouse, of which we only had 1 unique terabyte of data in there. So when we looked at this, we said, this is not a scalable solution. We re-architected from the ground up. We went to a production-only environment. But when I say production-only, I mean we develop in production. We have all of our data in production. We don't have lower environments for building and testing. We just develop policies and procedures and best practices to minimize risk to the system. And by doing that, we were able to go from 1 terabyte to 30 terabytes of unique data within the data warehouse. We're still looking at what we have here. We expect that over the next year, it's going to double. And a reason for that growth is largely because in the past, when people would try to get stuff into the data warehouse, it was so hard. We re-architected things so it's very easy to scale our data warehouse, to add new data into it. The more we delivered to people, and the faster we delivered it, the more people asked from us. And so, in some sense, you can argue we're victims of our own success. If we weren't doing a good job, there's no way we could have supported this kind of disk usage. So we have some challenges, though, when you get to this kind of scale for a data warehouse. Direct querying of data becomes slow as your tables get larger and larger and you have more things that people are joining across. So we want queries to generally get faster results for people. We want lower latency of data. So our ETL processes, we're refreshing data 24 times a day from all of our production systems. I should say from database proxies of production, not the production system directly. So like log ship databases, mirrors, availability group replicas, slaves, things like that. So we're loading 24 times a day, so we're current through the end of the hour every hour. That means we have a sliding latency window of maybe 20 minutes to 80 minutes for most data sources. And because we're refreshing 24 times a day, we have a very large workload pounding our servers. And we want to make sure that we can load data even faster. We don't want our server to have insufficient resources so that we then have to refresh less frequently. We want to make sure the server can handle pounding it as frequently as we are. We need to also support a mixed workload. So some of our users are running queries where it's point lookups. They want to know information about a specific order, about a specific customer, about a specific product. And then that same internal customer may want to run a query on, I want total sales for the last 5 years for this customer, for this region, for this sales organization. I want to know all of the phone call activity that's occurred in this site by customer representative or something like that. So we need to support point lookups as well as highly aggregated queries. So the resolution for us for some of our largest fact tables, and by some I mean I believe it's 29 of our fact tables, we went to clustered Columnstore indexes. The goal of the clustered Columnstore index in replacing these large tables was, one, to minimize disk usage. We wanted to make sure that we would have sufficient space to continue growing. Okay, I mentioned that we're at 30 terabytes of unique data, but that doesn't mean I have 30 terabytes of disk that I can use, let alone disk for backups and log files and everything else that you need. So we needed to make sure that we were using the disk efficiently at our scale. We also wanted to improve query performance. As I indicated before, we have lots of different workloads, lots of users hitting it, lots of reports hitting it. We need to make sure that we wanted clustered Columnstore indexes primarily to improve performance and the disk space usage. The way that we went about doing this is we basically identified about 3 to 5 tables that we thought these are our first candidates. Candidate tables had to be large tables, and they had to be more fact-based. By that I mean we had some very large tables like asset tables that contain metadata about the 170 million assets we have. And that's not exactly data that anyone would really aggregate off of. Mostly they'd use it as a dimension and they would join that to a table that actually has sales, views, orders, impressions, things like that. So we focus primarily on large tables and fact tables, things that would benefit from being able to be aggregated. The method we went about converting tables is we created new empty tables. So one of our concerns was that this is new technology. Is it going to work for us? If it doesn't work for us, how do we go back? How do we make this seamless for our internal customers? We know we're basically doing a rolling deployment in production of this technology, and we need to make sure that we are not jeopardizing the quality of service that we deliver today. So by creating separate tables, we could load the separate tables with the data through ETL processes in a minimally impactful way in batches so that we don't blow out our transaction logs. And then once the tables were loaded and completely synced with the real tables, we just did an SP rename to swap it out. Old table gets named to old, new table gets the original name. And then after we let the processes run for a while, we had our ETL processes loading the table for a while. We had users querying the tables. We monitored report usage data. We emailed people that we thought might be impacted by these things and said, let us know if you notice anything slow or odd. And basically, as we went through this process, once we verified that there were no real negative impacts to what we were doing and we were happy with the results we were getting, at that point, we then deleted the tables and then shrank the databases, rebuilt indexes, then shrinking databases causes fragmentation, and then again, continue to monitor performance and try to remediate any poor performing code that was identified. And we'll talk more about that. By and large, though, the most expensive thing of doing this whole project, it's not building the clustered column store index. That's easy. Create clustered column store index. Actually, it's just create the table, load the table, and then create an index. Pretty simple stuff. The biggest problem was really monitoring performance. We needed to have the framework in place. We already did, but we had to have a framework that allowed us to analyze usage of the data and be able to understand if users are getting slower performance, what conditions that occurs, or if they're getting faster performance too. So analyzing data was the slowest, most time-consuming part of this project. The results of now at the time of this slide, I focused on the 20 first tables that we converted. Since then, we've converted additional tables. But of the 20 tables, all of them were originally page compressed. And we were getting compression rates of around 28% on those tables. So these tables before were more like around 6 terabytes of data. As page compressed, they were taking up about 1.6 terabytes of data. And after we converted them clustered column store indexes, they were 172 gigabytes of data. So our compression rate was around 11% of the page compressed data, actually. So anyhow, most of the savings came from elimination of non-clustered indexes. Now that was a bit surprising. It was a theory we had, but we weren't really sure. One of the advantages of clustered column store indexes is basically each column is indexed, right? So if you don't have then lots of non-clustered indexes like we typically had in the data warehouse that we needed as covering indexes for common queries. So it turns out that our data on page was one set of disk, and then we had all of these non-clustered indexes. By going to clustered column store indexes, you eliminated all the non-clustered indexes, and the compression itself is higher on the tables themselves. So we saved most of the savings came from elimination of non-clustered indexes. We found that in general, we saved about 50% of disk over page compression. Okay, so this is a graph of some of the tables. And you can see over on the left that the blue bar represents the original page compressed size. And then the second bar represents the clustered column store index size. So in the case of the first table, we went from about 160 down to just over 20. And you can read this graph as well as I can speak about it. But you can see that clustered column store indexes were generally a fraction of the size of the original table. Now what's interesting to me, though, is to point out which ones were they a higher percentage of the original table. Those ones tended to be tables where the data didn't have a lot of consistency in a lot of patterns in the data. So some of the tables we had, basically, there just wasn't very much patterns for the data to compress well on. But even still, we saw compression benefits. And as you can see, it's a lot. This one here, though, was an outlier. This one was a single table that it was almost 900 gigs. And it compressed down to, I'm trying to recall, I think it was around 50, 55 gigs, something like that. So you can see that the compression we had on this was an outlier. It was exceptionally high compression. And there was a really good reason for this, though. It turns out that there was a lot of repetitive large string data in this table. This was a table that represented views of a particular product that we launched in 2014. And so it had, every time someone would go to a web page, it would collect what page were they on when they were viewing an image, and what domain were they on, and other information, because these were for images embedded throughout the world. And what we found is that we'd have hotspots of activity. Someone would embed an image of, like, I don't know, the new Princess Charlotte, right? You can imagine that there's a lot of people viewing it in a small amount of time. And they're all viewing it on the same pages generally. So a lot of the activity that happens, say, today, would be focused on those brand new images that everyone wants to see. Whereas some of the images that were hot, a month ago, hardly anyone looks at anymore. People look at fresh content and they do it in spikes. And so there was a lot of duplication of values, of very, very long string URLs that all compressed down to a tiny little thing. So I believe that this means that if you know you have an outlier table like this where there's data that has a very high degree of patterns in it and they're oversized data types, you'll see huge, ridiculously huge benefits for using cluster Columnstore indexes. We did some performance testing. So I've talked a bit about what the storage savings were. And as you recall, that was one of the two goals we had with implementing cluster Columnstore indexes. This is the other side of it, of trying to analyze, did we get the performance benefits for queries? So what we found is that highly aggregated queries did perform better, and substantially better. 2 to 20 times was very common. It varied wildly depending on what people were doing, but typically we saw these types of benefits. We found that point queries, looking up a specific order, a specific customer, things like that, where you're just returning a very small number of rows filtered to a specific key value, those queries tended to perform a little bit more slowly. But we're talking about queries before that took 0 to 1 seconds going to 1 to 2 seconds. So we gave up some performance, but from our end user perspective, it was negligible. We did find there were some extremely poorly written queries out there. So this was kind of a good way to detect bad code. Okay, so someone who had a query that used to take 30 seconds or a minute, and then you get actually it was more like when someone has a query that's takes an hour, and then now it takes 2 or 3 hours. We'd look at and say, well, this is because this query is awful. We really need to rewrite this, and then we'd get it down to 5 minutes. So this actually helped us find bad code. But once we did the rewriting of queries, we generally again saw that queries were faster. Now, this is a typical query performance. So in the first 3 bar graphs you see over there represent point queries. And as I mentioned before, the cluster Columnstore indexes tend to be slightly slower. And this is measured in seconds. So an example over there was a query that may have taken 30 seconds, went to 40 seconds, that kind of thing. Whereas the queries in the middle, these were, let me step back. Those are ETL queries. So here's one of the things we found with cluster Columnstore indexes is when we would merge the data from our staging to target tables, we would get slower performance, 10, 20% slower performance for an insert, update, delete statement. But those queries are already tuned and they're very fast already to begin with, so the cost was relatively negligible. Whereas if you look over here on the middle section, these were report queries. We saw that something might take a minute, might take 2 minutes, even 3 minutes or 4 minutes, and they came down to, sub 15 seconds, sub 20 seconds. And then the ad hoc queries, these were things where someone is writing SQL. They may have written SQL 9 years ago, and it slowly evolved as data warehouses were built and replaced, but it's some script that someone runs like through Management Studio or a tool or through some extraction process. And these were general benefits we saw. So lessons learned. Point lookup queries perform minimally worse. You should expect that they can be worse, but we're talking about a very, very small amount of performance overhead for being clustered Columnstore. Some covering non-clustered indexes and filtered indexes performed better than clustered Columnstore indexes. So if you knew that you always needed orders for a particular product, and you always needed this query to run, sometimes we would have created a derived table or an indexed view or just a filtered index because we knew this query is going to be executed every single time, and it's just a tiny fraction of the data. And what we found is clustered Columnstore indexes, for those particular use cases, performance was worse. We did mitigate that issue by building derived tables usually. I think there were maybe 3 examples of that happening out of the tens of thousands of queries that are executed in a given month. Merge statements. Now, I mentioned that merge statements were impacted a little bit, that there were performance issues, 10 to 20%, but there were some merge statements that were much more. They had a much worse performance. And what we realized is that this would happen when the query plan came back with a query plan where it thinks it has to unpack every single row group. So basically read out the whole entire table and then do the comparison and insert and update. And so these were corner cases. I think we may have had 3 or 4 of these out of the hundreds of tables that we load. Well, we only converted 29, so I guess 3 or 4 of them was about 20, 25%. And we resolved the issue by converting those to separate insert and update statements. And by doing that, the query optimizer was smarter. It knew what it needed to do better. A drawback, clustered Columnstore indexes, a limitation of it in the 2014 implementation, is that it only allows you to have the clustered Columnstore index. You cannot have any non-clustered indexes on that table. A primary key is another type of index. So you cannot have a primary key on these tables. So in order to make sure that we dedupe our data, that we enforce uniqueness of our data, that we don't pollute our data, we had to develop an ETL process that would then go out and basically look at recent records that have been inserted and then check across the whole table and make sure there are no duplicates. And then also on the weekend, we also have a process that goes through and just checks the whole table for any duplicates, alerts us so that we can fix the problem. I think in the year plus that we've been doing this now, it's we had maybe 3 instances of duplication that process has detected. Another lesson learned here: availability groups. In 2014, if you have a clustered Columnstore index in your database, and your database participates as a replica in an availability group, the readable secondary is not a queryable table. And that was kind of a big deal for us, given the architecture that I described to you before. So the way that we worked around that issue is we moved all the clustered Columnstore indexes into its own database. And we did this actually substantially after implementation. We were running our reports off the primary for a while. We eventually built out the clustered Columnstore index database, swapped all the object references to point to this new database, and then we maintained the second version of that identical database on the secondary through ETL. And then that makes it readable because it's no longer part of an availability group. SQL Server 2016. So we've talked about that. We're part of the TAP program, so we have had time to experiment and play with SQL Server 2016 in its various CTP forms. And what we found, first of all, our request, our ask, when we was that that it should be readable in a secondary. It's the first thing we asked back in December 2013. It's in the next version of SQL Server. We tested it functionally. It works the way we expect it to. So we're very much looking forward to going forward with 2016 so we can eliminate the Band-Aid solution that we implemented and just have clustered Columnstore indexes in our AG. Non-clustered indexes can be created in 2016. Now, this was a big deal for us because you can create a unique non-clustered index. A unique non-clustered index will enforce uniqueness of your data. So we did go ahead and create these in the test lab on our databases. And we found that on average, it added about 35% of storage overhead to the clustered Columnstore indexes. Now that meant our compression rate went from around 14% to 19%. So we're still getting disk savings over being page compressed. Page compressed, we typically are around 28%. So for us, we looked at this and said, this is acceptable to be able to enforce uniqueness. Another thing, too, was I was a bit surprised about the speed at which we were able to create the non-clustered indexes. So we have 4.3 billion rows of data, 100 gigabytes of non-clustered indexes that we built across 15 tables, and it took about 30 minutes, of which 20 minutes was one table. It was that outlier table that I showed you guys before. And I'll talk to you about why it took so much longer. But the rest of the tables, well, let it speak for itself. The left blue bar represents the clustered Columnstore index size. The gold bar in this case is the unique non-clustered index, the primary key, basically, that we were creating. And then the green line is the duration in seconds it took to create the unique non-clustered index. And what we found is that it wasn't the number of rows or the size of the original table that determined how long it took to create one of these indexes. It was really the size of the non-clustered index itself. So if you look on that first table, that non-clustered index was on an integer field. It was a very small non-clustered index relative to the whole table size. But then you look at Table 2 and Table 4, and you see that the non-clustered indexes were 5 times larger than Table 1, roughly. And so the duration, it took longer to write the non-clustered indexes out. Overall, though, we're very happy. This is measured in seconds on the right. So you can see that even for the largest tables, the longest table duration, we're talking about less than 3 minutes to build an index, with the exception of that one outlier table. Now, that one outlier table, the one that had the awesome space savings, its key was a varchar 22, and it was completely randomized. Uppercase, lowercase, case-sensitive random key, which means that it's actually more random than a GUID, right? So when we created the non-clustered index on that, it actually ended up being fairly large relative to the table. It's about 40% of the original table size, of the clustered Columnstore index table size. And that one took, like I said, 19 minutes and 5 seconds, I believe, to create. So I'll hand it off. Any questions, though, before we go on? Okay.
Great. Thanks, Jack. Okay, so in the last piece of the session, I just wanted to talk about kind of broader lessons learned that we've learned kind of in talking to customers across their deployments and some of their scenarios. So we'll start with in-memory OLTP. I'll do a couple of lessons learned here, and then we'll talk a little bit about some of the Columnstore considerations. So the first question that we typically get asked for in-memory OLTP is comments like, hey, I have databases sizes of a terabyte. Is that going to work with in-memory OLTP? You kind of saw from the care group example as well that they basically just moved 1 out of 7 tables, right? You don't have to move your entire database in. They just picked that real hot data set, which in their case actually was flowing data, right? And they kept it at about 20 gig in memory. In terms of most of the deployments we've seen on the high end, maybe 30, now up to 40 gig in memory. So customers have databases well over, in care group's case, over 100 gig et cetera, but very small subset of that is utilizing in-memory OLTP. Hardware requirements for high performance. All the customers that we have deployed in production are using what I would deem commodity boxes, 2 sockets or 4 sockets. Probably a few more on 4 socket than 2 sockets. Some were actually running on bare metal, others running in VMs as well. The I/O subsystem latency, and we talked about that a little bit before to this gentleman's comment, still very important to consider, particularly in schema and data implementations. So there are a number of workload patterns where in-memory OLTP has proven successful. I have a pointer to a paper that talks about some of these patterns in depth. The first one, session state. Actually, the development team, we wrote kind of a sample model on CodePlex of ASP.NET session state. It's got a specific driver that you can use to basically optimize for in-memory OLTP type implementations. High data insert rate, read performance and scale, compute-heavy data processing, a lot of computation in your T-SQL. If you can move that into natively compiled store procedures, you can get some tremendous gains and low latency. Again, if you can move that into native compiled store procedures as well, some tremendous gains there around latency. That's where you can ultimately get up to the amazing numbers that we've seen on kind of the 20 to 30x type gains. So these last 2 components have some considerations around that. In-memory OLTP is not going to address every single bottleneck or every single consideration that you may have with the solution going against a database. You get gains specifically in the query execution layer and the data access layer. It does not address anything in the networking layer, or unless you're doing schema only in that logging type layer. We will have less logging in the transaction log, but the latency is still there for that type of I/O. And the last consideration or recommendation here is, again, the entire database doesn't need to be migrated to in-memory OLTP. You want to kind of take a staged approach to that migration. So I'll just address the last 2 data points around migration considerations here. So on the left, or on your left here, you have the traditional execution stack. Again, we have client connectivity, query execution, the buffer pool, in essence, data access, and the transaction logging type behavior. So really where you're going to get the gains, in general, say the 2 to 30x types improvements are really in that data access and the procedure execution layers. And in terms of migration considerations, recommend a staged approach. There were a number of people that went out right away and kind of said, oh, we're going to put everything in the database into in-memory OLTP. So you really want to identify the bottlenecks in the tables. In the care group scenario, we talked about that. We talked about some of the tooling you can use to do that. You can also query some specific DMVs to basically understand and think about your workload patterns and how they might be applicable to in-memory OLTP. You want to address the unsupported constructs and migrate the data. Again, first step, look at the memory optimized tables. You want to ultimately perform the minimal amount of changes and then have interpreted access. So not necessarily convert to natively compiled store procedures, but just have the data in the memory optimized tables and see if that's enough for your particular application. If not, or you really need to get the T-SQL into natively compiled store procedures, you want to identify those performance critical transaction code pieces, address the surface area there, and migrate the code. Again, circle here is this should definitely be an iterative process. You probably want to start with one. You may actually alleviate the bottleneck there, and you may incorporate and find another bottleneck further down in the process as well, now that you're getting more scale, throughput, et cetera. The last consideration that I wanted to call out here is very important to test with a realistic workload and think about what you're ultimately trying to get at in terms of performance gains. So I don't know if a number of you were in the instructor-led lab this morning, but for in-memory OLTP. But the example here is basically just saying that if you test something like 1,000 inserts or 2,000 inserts into a memory optimized table, you're not going to get 30x gains. In particular, some of the major gains that people are seeing is when they have a lot of contention, right? We can avoid the locking, the latching, and we can get much greater scale. So a good example of this, we actually published an AdventureWorks database and a workload that you can run against that. The AdventureWorks database is converted to in-memory OLTP. And again, if you just run a single execution of a particular call, there's no contention, there's no real bottlenecks in the engine, you're not going to see that much gains. You can see here, in running a workload that we have against that AdventureWorks 2012 in-memory OLTP conversion, basically, in this particular case, once you get up to greater than 20 threads, which is where you start having a lot of contention, then you can see basically dramatic gains between in-memory OLTP, that bottom line, and where the duration will just go up and up and up in the disk-based type case. So thinking about testing with a realistic workload, in particular when you're thinking about scale, is very important. You just may not see the gains otherwise. So let's talk about Columnstore a little bit and some of the lessons learned here. So data loading considerations. I think probably in some of the other sessions, Sunil may have talked about this a little bit, but batching of data to go directly into the Columnstore and avoiding row groups, very important. Ideally, if you could choose, you'll get that if you choose a batch size greater than 1 million rows. And for bulk insert, it's a little over 100,000. So if you're using the bulk API or anything like that, go a little over 100,000, you go directly into the compressed Columnstore index. There's no data, or there's no ordering of data within Columnstore. We'll work around for that. You may want to load data into a clustered index that's aligned with the query patterns, the primary query patterns that you're seeing there. Then you can create the clustered Columnstore index with drop existing. So get some ordering there that would match your primary search criteria. The updates are logical, so that means they're basically delete insert pairs. If you have heavy update workloads or heavy delete workloads, but it's typically seen in update workloads, you may need to think about rebuilding your indexes really to regain space and potentially increase performance there. Concurrency, the blocking granularity is at the row group. So in each row group, we have about 1 million records, give or take. Columnstore, cluster Columnstore index in 2014 is not really built for heavy OLTP workload environments. So definitely you want to potentially try and avoid that heavy read-write workloads with your queries as well. In particular, if you're not doing queries on with like a read uncommitted isolation level. And compression. But actually before that, I'll just mention that in particular, scenarios such as 2, bit of 3, and 4, if you haven't seen it, we're looking to address those in SQL 2016 as well. So compression. Again, Jack talked about this a lot. Care Group brought this up as well about the space savings that they ultimately got. So these are just some of the general gains that people have seen around compression. So typical compression against raw data, about 5 to 8x. Of course, you have your anomalous cases, be it positive or less, but 2 to 4x over page compression is what we've typically seen. Using archival compression, which is a feature that you can build in the cluster Columnstore index. You can build it with archival compression. Allows for further space savings. We've seen about approximately 20% gains on average over that. And backup compression will give you further gains on your backup files with the cluster Columnstore index. It actually uses a little bit different compression algorithms. So up to 2x gains on your backup files above and beyond the cluster Columnstore index. Space savings. So query performance. Jack talked a little bit about this on the singleton or point lookups don't perform as well. There's no seek operator within the Columnstore index. In most cases, and we definitely have other customers that have said, hey, yeah, we basically had the same problem. We have a small percentage of our workload that's basically trying to do these point lookups and gotten worse performance. In the majority / every case that I've seen, people have ultimately said, hey, this is working great for a large percentage of our queries, and we're very happy with it, and it hasn't been unbearable in terms of moving away from the cluster column store index. Queries where search predicate as a string column. We don't have predicate pushdown for string columns in SQL Server 2014, so that can result in a scan. Can be pretty impactful around query performance. There's some consideration around there that you could look at doing, basically getting that string column potentially out. That's also something we're looking at addressing in SQL Server 2016. Batch mode queries are ideal for good performance. So ultimately, right, we can batch those records up into memory all at once. You can get some significant performance gains in that case. There are some constructs that don't participate in batch mode. Serial queries, any windowing, over clauses, multiple distincts. Again, just to comment, all those are actually, those three are all addressed in SQL 2016. And a general recommendation is partition when possible, as that can even further enhance performance. Of course, we're working with very large data sets, so partition can be very nice in terms of data movement, et cetera, and partition alignment can help out as well. So in one case, some examples of this, it can speed up loading of data. Again, you could load into a staging table, create your cluster column store index. Cluster column store indexes are fully supported on partitions. You can create them on a particular partition. You can use them in partition swapping and management, et cetera, as well. This allows as well for partition level rebuild of a column store index if you have the column store index over your partition scheme. It also allows for partition elimination in queries. So we can, again, potentially on certain queries remove large percentages of the data that we would have to go over on that query. And data archival obviously can be easier. So I just have one more example of that consideration. So I was working with a customer. I actually happened to mention this in my session yesterday. It was the NASDAQ, and they had about a 9 terabyte table that they wanted to convert to Columnstore. So just want to talk about a few of the considerations there. The table had about 62 billion rows. It was partitioned daily, approximately 35 gig per partition, so about 255 partitions in the scheme. They actually did, when they were initially looking at it, have 4 varchar max columns. So again, cluster column store index in SQL Server 2014 not supported on LOB data types. So that was a problem for them, but they really wanted to go to the cluster column store index. They saw great gains, potential, and realization when they actually went to it in terms of query performance, in terms of space savings, et cetera. So to address the varchar max columns, they did some analysis, kind of as Jack talked about. It was a forcing function to them to really assess, all right, what are we storing in here? What do we really need, et cetera, et cetera. And they realized actually they didn't have any data that was greater than, I think, 4,000 characters. So yeah, but hey, I have a 9 terabyte table. So how do I change the varchar max columns? And how do I create a clustered column store index? So some of the considerations there. The first step that they actually went at, they tried alter table. I don't know if others have tried alter table on a very large table. They tested it. Took about 10 hours per partition. They estimated it would take them about a third of a year to do. Not really viable. They tried to insert select into, dropped down dramatically, about an hour per partition. So that was 10 days. We took advantage. We ended up taking advantage, and again, the partitioning helped out dramatically, certainly even in the insert select into case. Couldn't imagine doing any of this on a 9 terabyte in totality table. We took advantage of a feature, maybe little known, parallel select into, which is another feature of SQL Server 2014. So we did a parallel select into per partition. We did alter the file group because as you're doing select into, we didn't want it to go to the primary file group. This took 11 minutes per partition. So basically, by utilizing these partitions, by basically doing select into, got rid of the varchar max columns, moved all the data over. Do be a little bit careful with it. Obviously, it can truncate data as you're doing this, but we did the converts in line in the select into. And partition by partition, we moved it over. So this went along with basically ultimately moving over the database size of 500 terabytes raw. But this was their largest table, approaching 9 terabytes raw today. So just another kind of practical example of how Columnstore is really helpful. Customers really wanted to move there. And some kind of tips and tricks on the way we did it with a really, really large table. So with that, just quickly in the middle section here, actually a number of the related sessions. There are the in-memory OLTP labs that are available throughout the conference. I would encourage you, if you're interested in that technology, to go and look at them and get some practical experience with that. 4 pointers up top. The common workload patterns and migration considerations is a white paper. Talks about a lot of the common workload patterns for in-memory OLTP that have been adopted. Data loading performance considerations, again, that's a CAT blog that we just released. Very helpful in terms of considerations in data loading into clustered Columnstore index. And some pointers on the in-memory OLTP session state provider and the adventure works that I talked about earlier. So with that, definitely open to any questions and appreciate the time. And please evaluate this session.